Hello everyone. Let me first check if you all can hear me. Please send me a yes or a okay in the question box to make sure the audio system is working. Perfect. Let's get started then. So I want to thank all of you for attending this webinar. I am Stephane Boubanga Tombet, currently a feed application scientist for Telops. Today, I wanted to share with you some of our work on real-time airborne gas detection using thermal infrared imaging. I will try to fit within a 30 minutes talk, and after the talk I will take your answers. So please use the question box to send me your questions and I will answer to or respond to it directly today. And depending on the number of questions I will receive, if I receive a lot of questions, I will gather all of the questions and do a kind of question and answer document, and I will send it to you along with this recording sometime later next week. So Telops actually is a company founded in 2000 in Quebec City in Canada. We are about 60 employees, including PhDs, masters, and engineers, shared between Quebec City, China, United States, and France. At Telops, we produce scientific instruments. We design and manufacture high-performance, hyperspectral imaging systems, high speed and high definition cameras. We also offer research and development services in order to respond to the specific needs of our customers. Our product, our cameras can be classified in 4 different categories. 2 spectrally resolved cameras, including hyperspectral cameras with high spectral resolution, user scalable between 0.25 and 150 centimeter -1, and multispectral camera with a fast rotating spectral wheel, splitting signal into different spectral band, allowing for time resolved multi-channel imaging here. We also have 2 broadband cameras, including high-speed cameras here with more than 10,000 frames per second in our recent model called M3K, but also high dynamic cameras here allowing continuous acquisition up to 2,500 degrees Celsius. We put the focus on high-speed cameras for broadband cameras here at Telops, and for spectrally resolved cameras, we are leaders in the market. And the markets we are targeting also can be classified here in 4 different categories. As you can see here, defense and security, national labs and institutions, universities, and industry. The work I will be presenting today was done on hyperspectral imaging system, and this scientific instrument we also called Hyper-Cam. Here is a lightweight and compact system of about 32 kilograms here. I will get back to some of those features here in the next slides. This instrument is based on Fourier transform technology, FTIR here, and we have long wave and mid wave versions of it, and the detector here feature closed cycle Sterling cooled detector with 256 by 320 pixels. Here the spectral resolution here, as I mentioned before, is a user scalable, here down to 0.25 centimeter minus 1 with 1,600 channels in the very long wave and 19,000 in the mid-wave extended here. So if you are looking for an almost backpackable hyperspectral instrument with high spectral resolution, high spatial resolution, and high temporal resolution, this is the best suite for you. This is the best instrument, and this is the instrument you need to be using here. The data recorded by this instrument here is called Hypercube. They are three-dimensional data, meaning that there is two image spatial dimension x and y here, and the third dimension here is a spectral dimension. And during the operation of the instrument, as illustrated here, the moving mirror here sweep between the zero path difference here at constant velocity as a function of time, and a full interferogram is recorded as you can see here on each pixels of the image here, and with the Fourier, with the interferogram here, a fast Fourier transform is performed. Here we also do automatic calibration using the integrated black bodies in the Hyper-Cam here, as you can see here, the cold black body and hard black body here, and this radiometric calibration and lead to calibrated spectra here. So during experiments here, you will have real-time calibrated data. Those instruments here, our Hyper-Cam, can be used both in ground-based, as ground-based with tripod, as you can see here, for example, for volcanology. Here in this picture, I show here one of our field application scientists, along with some other scientists, French teams, climbed the Stromboli volcano in Italy to take hyperspectral thermal infrared footage of volcano eruption in the allowing identification of multiple gases such as sulfur fluoride, silicon, sulfur dioxide, and silicon fluoride coming out of the crater there. We also propose airborne solutions here on those solutions, high spatial and high spectral resolution hyper maps can readily be obtained for geological survey, for example, for pollution monitoring, and for surveillance applications. The work I will be presenting today was done on the airborne solution. As you can see here, the Hyper-Cam can be easily mounted on an airborne platform, and the installation is very fast, takes only a few minutes to be mounted there, and the platform is equipped with a GPS system unit. Is here in red. You see they're providing geolocation, altitude, and timestamp information. Sorry, timestamp information in there. Also an image motion composition mirror shown here that allows composition of the aircraft forward motion, pitch, and roll. And also a laser range finder here in gray here that provide altitude relative to the ground, but also a rotation stage that compensate aircraft yaw and here passive vibration damping there. Normally, acquiring a full interphotogram with our Hyper-Cam will take typically 1 second. Here, we therefore need to be stable here during that acquisition time. So the image motion composition mirror uses the GPS data to compensate efficiently the aircraft movement during the acquisition. The data here include the relevant informations on ortho rectifications and stitching of the images there. Visible images are also simultaneously recorded along with data cube here using both side CCD camera on the platform. Here the CCD camera is run here. Concerning the project I'm presenting today, the flight, sorry, was taken. The flight was done above the Telops building. As you can see here, some pictures of the Telops building done with our long wave sensor at the speed of 110 knots. Here, this image here at 2,350 feet. You can see the Telops building in here, the outs and here at 4,650 feet, the Telops building as right here. The outside temperature was about 22 degrees, and the relative humidity was about 70%. In general, our airborne hyperspectral imaging offered two distinct acquisition modes, as illustrated in this slide here: mapping mode and targeting mode. Actually, the mapping acquisition mode is a representative of most airborne sensor, where individual images or data cube are continuously recorded as the aircraft flies above an area of interest. And the targeting mode actually takes full advantages of this image motion control mirror component I showed you a few slides back. As in this mode, one can record successive hyperspectral data cube of the same area of interest. Here, data acquisition is typically optimized here to record, depending on the ground speed, altitude, as many data cubes as possible while the aircraft approaches, flies above and beyond the target area here. So in the mapping mode, here data acquisition of the neighboring ground area is conducted, while in this allow covering in this mode allow covering of a large area of interest, and the overlap areas here allow efficient image stitching using orthorhombic procedure. Here, as you can see here, flying over those areas here. This is the staging of the image here using this auto rectification procedure here to obtain this all map in here. And this is an example of one of the map we obtain here, a very large map using successive acquisition of multiple area of interest. Here, this was done with our long wave detector here at 7,000 feet with 0.25 telescope here. This is an infrared image, and this is a visible image using the CCD, visible CCD camera. I told you I mentioned a few slides back, actually. And in the targeting mode here, as I mentioned, successive hypercube of the same area of interest can be acquired here, as you can see in this video. Here, this I think was a refinery. We took those data. This allow, for example, to get time-dependent information such as gas cloud dispersion, but it also can allow to improve signal to noise ratio by doing averaging here. Another part of the story that make the success of our airborne project here is the diversity and the richness of our softwares. We have mission planner softwares, the software here that was slightly updated recently, and in this software the user can select the spectral range for real-time calibration. In here we also have a Reveal Airborne software. This Reveal Airborne software here is the data acquisition software and allow real-time radiance calibration. Data acquisition and the data can be saved in a raw format, as you can see here, but also in calibrated format. This radiance.sic file here. We also have Reveal Airborne detection and identification, Reveal ADI software here that runs in parallel with Reveal Airborne software and allow the identification, detection and identification of calibrated data cube when the data cube became available, but also show real-time detection and identification result with the option of saving the report or detection reports there, and then the geo processing tools in here. This is an overview of this mission planner software. The big benefit of our system through the use of this software, in contrast to conventional push-button system, here is the flexibility. You can here change a whole set of parameters such as spectral range, as I mentioned, spectral resolution, spatial resolution, while in push-button system you end up being stuck in a single configuration. And this here is an overview of the Reveal Airborne software. As I told you, this is data acquisition software. This an example of one of the flight campaign we conducted a few times ago. When using this software, you can use the automatic mode here, meaning that if I launch the video here, that when you're flying, when you will reach the area of interest, this will turn green, or even before it will start to turn yellow, saying that you're close to this area of interest. And then and now it's yellow, that you're close to that area of interest, and when you and the area of interest turn green here, and acquisition will start. Here, this is the number of acquisitions, and when you will be close to be out of that area of interest, it will turn green again to tell you that you're ready to go out of this area of interest. Then But you also have the possibility to use this in manual mode, and in that manual mode, you just have to press start recording, with this here when you reach that area of interest. Now you, as you say, you turn green because you were going to be out of that area of interest. This also provides you some useful real-time information such as the current speed, the altitude, and so on. We also have some detection and identification software here that we use for real-time detection and identification here, but we can also use this here for post-processing. Here, this reveal DNI for detection and identification uses a separate software here, but we have updated this and used it as a plug-in in a Reveal Pro software. The Reveal Pro software is the one we use for grant base. Here in the database, here you can select targets. Here, for example, methanol solvent pills. Here, this software where was then integrated in the airborne solution, so that it can run in parallel with the Reveal Airborne for detection and identification. During the flight, actually the Reveal Airborne will provide flight information useful to guide the aircraft pilot, mainly regarding the speed, the altitude, the aircraft pitch, as I mentioned a few slides back, and the Reveal ADI airborne detection and identification include a LED to know if the flight parameters goes outside of the allowed range. So for the project presenting today, as I mentioned before, we flew above the Telops building, as you can see in here on the parking lot of the Telops building. We had a methanol dish, acetone dish, and ethylene release points, as you can see in this picture here. And the goal was obviously to detect those gas when aircraft passes above those release points here. And during the flight, as I mentioned, also that the Reveal ADI airborne detection and identification software generate this kind of reports. Reports you can see in here, and when the gas is detected, you can see the gas in the report in here as, for example, here with the image pixels where the gas is detected here. And for this campaign, we flew, as I said, at the altitude of 2,350 in mapping mode. Here with the spectral resolution of 4 centimeter minus 1, we were able to successfully detect the acetone here on 44 pixels, ethylene and methanol here. But also at a higher altitude, 4,650 feet with the same spectral resolution, we were able to detect ethylene and methanol in here. But also but because I told you that we can fly we can do acquisition in mapping mode, but also in targeting mode. Here in targeting mode over 16 consecutive data cube here at 2,350 feet with the spectral resolution resolution of 8 centimeter minus 1, we were able to detect ethylene here on some 60 pixels there. In this flight campaign, we also flew above a refinery. Here, this other slide here, I'm showing you in the mapping mode, actually, at the same altitude here of 2,350 feet with the spectral resolution 4 centimeter minus 1, and above this refinery, as you can see here, we were able to detect flares of CO2 and SO2 emission. You can see here, and this reveal ADI, airborne detection and identification, is included in our 2018 catalog. So it comes to the conclusion today. I hope I convince you that with our hyperspectral imaging technology hold great potentiality for large number of applications. We have flexibility here with our systems. Spectral range in mid-wave infrared, thermal infrared, from 3 to 5 micron and from 8 to 12 micron. Actually, the spectral resolution is user scalable, and acquisition modes, mapping and targeting. Mapping is a little bit more common, and targeting is specific to our systems here. And our system can be used in ground-based and airborne, as I am presented you today, with high spectral resolution provided by the FTIR technology, including in our system. But we also provide actually temperature emissivity separation solutions. Here we called flash IR, which will also come in, which is also included in our 2018 catalog. Here is flash IR, allowed to do emissivity, temperature emissivity separations on any kind of scene you can have in there. And I also hope that I convince you that the selectivity provided by the spectral resolution of our system and along with our softwares, airborne software solutions, allow real-time chemical identification of gas cloud with good accuracy. Actually, quantification can be conducted. I didn't present the quantification result today, but we've done a lot of quantifications. We can discuss about it in a question part of this webinar, and I can direct you to some of the white paper we've done on the quantifications of this airborne campaigns here, and send you some of the paper. So the result we've got illustrates the potentialities of our airborne hyperspectral imaging for efficient characterizations of gas plume over a large area, actually, and the airborne targeting mode, which is a unique feature of Telops Hyper-Cam. Here can bring valuable information such as time-dependent information, but also can helps you to have increase your signal-to-noise ratio, as I mentioned, by doing some averaging after you've done taken a lot of acquisitions in there. We at Telops also provide rental services. If you have an idea of any project you want to conduct, you can come to us. We can advise you, direct you to the right equipment for you, and one of our field application scientists can come with the equipment, take some, do some experiments with you on your project. But also that if you want to do your experiments by your own, we offer some trainings on our Hyper-Cam or even all of our cameras. We can give you some trainings so you can go and do your experiments by your own actually. And I will stop here because my 30 minutes is done. I will take your questions and I will respond to your questions now on a one-by-one basis. But within the 30 minutes we have now, we can keep sending those questions in the question box, because I will come to you, answer to you. But if I didn't have time to get back to you, as I said, I will gather all the questions, do a question and answer box. I will send all of you with this recording of this talk. So I will leave you with this last slide here, where we have our field application scientists, our commercial people, the people you can shoot email to, and they will be happy to get back to you wherever you are in the world. You can we can get back to you if you contact us. Thank you very much. So we'll be happy to take your questions now. No, actually, the meeting didn't stop. I'm answering your questions. So if you have questions there, just send it because I'm going through it one by one. I'm still here for the next 10 minutes. So please keep sending me your questions if 10 or 15 minutes. Keep sending me your questions because I'm answering to it on one-on-one basis. Hi there. If you're still there, we still have like 5 minutes. Please send me your questions, and then in the next 5 minutes, I will stop the session. Thank you. Yeah, keep signing your questions. We still have like 5 minutes. Okay.